Welcome. Thank you for watching this video and studying math with me. Today's topic is radical expressions. So let's get radical. A radical looks sort of like a division sign with a little bit of a mark there, and that is called the radical symbol. The radicand is the role being played by 18 in this example, and the index of the radical is the number that is up here. In this case, that is called a cube root. If nothing is written, it is called a square root. It is just understood to be a square root, so I would call this a cube root of 18. Now, in terms of what we talked about with fractional exponents, the nth root of a number a is a to the 1 over n. This is always, in this class, a single real valued function, and if n is even, that means the nth root, the principal nth root, is bigger than or equal to 0. If n is odd, it can be positive or negative. And we can then turn from 1 over n to m over n, and that can either be the nth root of a to the m or the nth root of a raised to the mth power. Let's do some calculation examples then. So here we're looking at, this is going to be 27 raised to the 1/3, and 27 is known to be 3 cubed, and so I end up with 3 as an answer. And the next problem, we do the radical first, so this is minus, and then this is the 4th root of 10 to the 4th, and so the answer is going to be minus 10. And this problem, we're taking the cube root of negative 216, and 216 is known to be 6 cubed, so negative 216 is negative 6 cubed. Taken to the 1/3 power is going to be minus 6. Now here we're taking the 4th root of negative 81. There's no real number that will give us that, and so the answer here should be not real. Continuing with these examples, writing each root using exponents, and to evaluate, we're going to take the cube root of the numerator and denominator and get the cube root of 125 is 5, the cube root of 512 is 8. In this problem, we're taking the 5th root of minus 243 and then multiplying it by a minus. Again, 243 is 3 raised to the 5th power. So this is the calculation we will do, and a minus times a minus is going to be a plus. The directions here are, say, write in radical form and simplify. Here we have 16 to the 3/4. The technique is to take the 4th root of 16 first and then cube it. The 4th root of 16 is known to be 2, so the answer is 8. Here we're going to take the cube root of minus 64 first, and then we're going to square it. This is going to be a negative 4 squared is 16. Here, if 3/2 is the exponent, 121 is the base, and there's a minus in front of that. So the cube root of 121, 121 is known to be, let's see, first it's the square root. Notice that there's no index written there. So the square root of 121 is known to be 11. And then we're going to cube that and multiply by the minus sign, so the answer is minus 1331. Now here we're going to take the 8th root of x to the 7, but since that is an even root we're taking, we must insist that y be bigger than or equal to 0. Here we're supposed to write in radical form and simplify. If 4/5 is the exponent, then the base is z. So this is going to be 7 times the 5th root of z to the 4th. If minus 1/4 is the exponent, then the base is q. The negative puts it in the denominator, and the 1/4 means I'm taking the 4th root of q. So this is going to be 12 over the 4th root of q. Since I'm taking an even root of q, we must insist that q be bigger than or equal to 0 to be real. And this expression is, when I'm taking the 6th root, note that that is a sum, not a product, so there's no simplification I can do, and I just write the 6th root of 5x plus 2y. Here we're to write in exponential form. This is going to be n to the 3 over 7. Here, the 15 is not affected by the exponent of 4, so this is going to be 15 and it's going to be r to the 4 over 3. Here, what we have is this induces an exponent of 1/5, but underneath there's an exponent of 8. So I'm going to be applying an exponent of 8 over 5 to everything that is underneath the radical. And then I'm multiplying by -2. So the simplification is going to be -2, 3 to the 8 over 5, x to the 16 over 5. Again, here there is not really anything I can do because I'm adding instead of multiplying, so it's just going to be r squared plus s to the 4th, all to the 1/3. The last example is here. Now this 1/4 is over all of the 10x, so that's the biggest simplification that you really can do with that problem. Now, a little bit of a note, the square root of x squared is not really x, because consider the following example. X is equal to -1/6, then -6 squared, and then the square root is going to be the same as the square root of 36, which is 6. So you can see we started with -6 and ended up with 6. So the square root of x squared does not equal x, it equals the absolute value of x. You want to keep that in mind in these problems, because here we're taking the square root of z to the 6th. So what's going to happen is that's going to end up being the square root of this z cubed squared, and so that's going to be the absolute value of z cubed. Now here I'm taking the 7th root of t to the 7th. Those are odd numbers, so it is just t. It could be negative, it could be positive. Here we're taking the square root of 81, r to the 8th, s to the 10. So the square root of 81 is known to be 9. The square root of r to the 8th is known to be r to the 4, and the square root of s to the 5th is known to be s to the 5. But 9 is a positive number, r to the 4th is always a positive number, but s to the 5th could be positive or negative, so we have to have the absolute value there. Lastly, down here, when we do this, we will see that this is like our example before. It's going to be the absolute value of what's underneath there. The absolute value of -3 is going to be 3. Continuing with this, this is just going to be m squared. That's 10 over 5. Here we're going to have what is being squared underneath the square root is 3x minus 4. So it's going to be the absolute value of 3x minus 4. And here it's important to note we're taking the square root of, this is really in a factored form, is x minus 5 whole squared. So we're taking the square root of x minus 5 whole squared is going to be the absolute value of 5 minus x. All right, now we're going to be simplifying these expressions. There is a perfect, let's just multiply 5 times 45, we'll get 225, and the square root of 225 is known to be 15. You do want to memorize some of these to work problems quickly. Now here I'm going to have n to the 3 over 5 times n to the 2 over 5. Same base, we're going to add exponents. 3 over 5 plus 2 over 5 is 1. So it's n to the first power. And here I'll take the square root of the top and the square root of the bottom. The square root of 169 is known to be 13, so this is the square root of 11 over 13. Continuing to simplify here, I'm going to take the 6th root of the top and the 6th root of the bottom, and that's going to give me the 6th root of a over here. I'm taking the 6th root of b to the 12th is b squared, because it is 12 over 6. Here I'm taking 17, the 4th root, and then I'm taking the 1/5 root of that. So basically I'm going to have 1/4 times 1/5, or 17 raised to the 1 over 20 exponent, and that's the 20th root of 17. Here I'm taking 1/6 root of 8, and then I'm taking the square root of that. And so that is going to be the 12th root of 8, or 8 to the 1 over 12. Okay, simplifying these radicals, the biggest perfect square in 288 is 144. So I'm going to have 12 times the square root of 2. The biggest perfect cube in 125 is exactly 125, so that's going to be 5, and 5 times minus 8 is a negative 40. And here I'm looking for the biggest perfect cubes that are in each one of those. So the 64 is a perfect cube, a to the 6th is a perfect cube, b to the 6th is a perfect cube, and c to the 9th is a perfect cube. Now I do have some leftovers. I need a 2 times the 64 to get the 128. The a stands by itself, but then I'm going to have a b squared and c left over. These perfect cubes will come out as the cube root of 64 is 4. The cube root of a to the 6th is a squared. The cube root of b to the 6th is b squared. And the cube root of c to the 9 is c cubed. And this cube root is left over, and everything is left under the radical. Here we're supposed to add or subtract as indicated. Notice that there's a common factor of square root of 5p cubed. I can pull that out, so I have 14 of those minus 11 of those, and the net is going to be 3 of those. 3 multiplied times that. Here I will pull out the greatest perfect square. Here is the square root of 25, so there's a 5 coming out, and there's also a b coming out of here, and what will be left is still under the square root. Here we have b times, and there's a perfect square in 12, which is 4, so that means there's a 2 coming out. And so what will happen is I will have 5b coming out as a perfect square, left with the square root of 3ab minus, I will have 2b, and this is the square root of 3ab. So I have 5b times this minus 2b times that. I can factor that out, and I end up getting a net of 3b times the square root of ab. Doing another similar problem. This time I'm taking cube roots. So the cube root of 81 is known to be 3 to the 4th, so I can pull a 3 out. It's 3 cubed times another 3 that's left under the radical. Here I'm going to have x to the 5th, so there is a x to the, it is x cubed times x squared, so I can pull out the x, and I will have x squared left. And here I can pull out a y squared, because that will be y to the 6th. I'm left with a y. Now if I do the similar thing over here on this problem, I will have a cube root. The biggest perfect cube in 24 is 8, and the cube root of that is 2. Again, I do the similar thing here. I'm going to have x squared on the outside and x squared still under the square root. And here I'm going to pull out 1y, and I'm left with the cube root of 3x squared y. Now notice that I have the same factor here, so I can pull it out. Now in this case, this term is not like that term. It doesn't have the same variables and the same exponents, so this is the best I can do in terms of simplifying it. Here we're simplifying radicals, so this is going to be square root of 2. 5 over 10 is 1/2. Down here, each of these are multiples of 3, and so I'm going to get a cubed, b to the 6th, and down here this is going to be 4 squared, and this is going to be to the 1/3 power times, this is going to be raised to the 1/6 power, so this is going to be 2 over 18, or the 9th root of 4 in a simplified form. Here we're going to exploit and observe that we have a pattern of a minus b times a plus b is going to be a squared minus b squared. So here I have a plus b, a minus b, so this is going to be a squared, which is 11, minus b squared, which is going to be 17, and the net is going to be minus 6. Here we're going to just be multiplying. This times this is going to be 15. This times this is going to be minus 5 square root of 2. This times this is going to be 3 times the square root of 32. One should note that the square root of 32 does have a perfect square in there. That's 16. So that is 4 times the square root of 2. And this times this is going to be the square root of 64. So if I do all of that, I'm going to get 15. And I'm doing the simplification. I will have these two middle terms. That'll become, these two will become 7. Square root of 2. 15 minus 8 is 7. Sometimes it is important to rationalize the denominator, and in calculus sometimes you have to do this. So here, in order to get rid of the denominator, I will multiply top and bottom by the square root of 7. I'm multiplying by 1. That means I'm not changing the value of the fraction. So this is equal to 2 times the square root of 7. Root 7 times root 7 is 7. Now here, this is really the cube root of 3 squared. So I'm going to multiply top and bottom to get rid of that radical in the denominator. So I'm going to multiply by the cube root of 3 to the first power. Because when I take the cube root of 3 squared times the cube root of 3, I get the cube root of 3 cubed, and that's just going to be 3. In the top, I have to multiply. I will get the cube root of 4 times the cube root of 3, which is the cube root of 12. Here I'm taking the cube root of the numerator and the cube root of the denominator, but I observed that a to the 5th over a squared is just a cubed, and here I'm going to have b over b to the 5th is going to be b to the 4th in the denominator. Now that gives me b to the 4th in the denominator gives me b times the cube root of b to the 1. So what I am doing to rationalize the denominator is multiplying the top and the bottom by the cube root of b squared. That means in the bottom at the end of the problem I'm going to have b times the cube root of b to the 1, cube root of b squared. That's going to be another b, that's b squared, and when I multiply across the top I will get the cube root of a cubed is a cube root of b squared. So there is the answer to that one. In this one, I will take the 4th root of the top and bottom and the 4th root of the top and bottom. And so I will get this. And now, to combine these two fractions, I need a common denominator, which means I have to multiply this one, top and bottom, by x squared, because the least common denominator is going to be x to the 4th. I do that, and I get this answer in a simplified form. Last but not least, sometimes we run across a denominator that includes a binomial, 2 terms, and so here what we're going to do is multiply top and bottom by the same thing, 1, but again we're going to use the conjugate. So instead of having 3, we're going to use 3 minus root 5 over 3 minus root 5. And we'll take advantage of the fact that here I have a plus b times a minus b, so that is going to be a squared minus b squared. Now a squared in this case is going to be 9, and root 5 times root 5 is 5. 9 minus 5 is 4, and up here it's 2 times that, so I end up with a 4. I will cancel the 2 into the 4 to get 2, and this is going to be 3 minus root 5 all by 2. Thanks for listening, and remember, time is precious. Each day must count. Do the math. It will make you strong. See you soon. Bye.